June 7, 1944. Gold Beach, Normandy, France. British Major Alan Beckett stood on a beach that shouldn't exist. 24 hours earlier, this stretch of French coastline had been defended by concrete bunkers, minefields, and obstacles designed to shred invasion craft. Now, 20,000 tons of supplies per day flowed across it through a harbor that hadn't existed yesterday morning. The harbor wasn't captured, it was built, towed across the English Channel in sections, assembled under German artillery fire, and operational before the beachhead was fully secured. 2 million tons of concrete, 150 steel caissons each weighing 6,000 tons, 23 massive concrete ships deliberately sunk as breakwaters, and 6 miles of flexible steel roadway floating on pontoons that rose and fell with 18-foot tides. The Germans had calculated that the Allies couldn't invade without capturing a deep-water port. Their intelligence estimated that supplying an invasion force required port facilities capable of handling 12,000 tons daily. Cherbourg was the nearest suitable port. The Germans had fortified it with everything in their arsenal, confident that its capture would take weeks and that the invasion would fail before logistics could be established. They never imagined the British would bring their own harbors. The Mulberry Harbours, codenamed Mulberry A and Mulberry B, represented the largest engineering project ever attempted under combat conditions. The components were manufactured across Britain by 45,000 workers, assembled in staging areas, towed across the channel by 132 tugs, and installed on hostile beaches while the invasion was still contested. The scope was staggering, more concrete than used in all British construction projects during 1943, more steel than required to build 500 bombers, logistics coordination involving 20,000 personnel. When British Prime Minister Winston Churchill first proposed the concept in 1942, his military chiefs thought he'd lost his mind. Build artificial harbors? Tow them across the channel? Install them on enemy beaches and use them to supply an invasion? It violated every principle of military logistics. Harbors required years to construct, needed sheltered water, demanded stable foundations, and couldn't possibly be assembled under fire. Churchill's response was 2 words: they must. And he appointed one man to make the impossible real: the engineer who said yes. Brigadier Bruce White, Chief Engineer of the British Army's Transportation Directorate, received the assignment in May 1942 with a single sheet of paper outlining requirements that read like science fiction. Provide harbor facilities for 12,000 tons of supplies daily. Accommodate ships drawing up to 20 feet. Protect against channel storms with 12-foot waves. Function in tidal ranges up to 18 feet. Be portable enough to tow across 100 miles of open ocean. Be installable on hostile beaches under fire. Be operational within 48 hours of D-Day. The final requirement was implicit but absolute. Failure meant the invasion would fail, hundreds of thousands of men would be stranded without supply, and the war would be lost. White assembled a team of engineers, naval architects, and construction specialists. Their first calculation was sobering. A harbor capable of handling 12,000 tons daily required a minimum of 4 miles of protected waterway, at least 20 berths for large vessels, breakwaters capable of stopping Atlantic storm waves, and flexible pier systems that could accommodate 18-foot tidal ranges while remaining stable enough for heavy trucks to cross. The engineering challenges were unprecedented. Conventional harbors were static structures built on stable foundations. The Mulberry Harbours would be floating structures, assembled in the ocean, subjected to waves, currents, and tides, while supporting loads that would destroy anything less than massive. Every component had to be strong enough to survive Atlantic storms, light enough to be towed by available tugs, stable enough to assemble in open water, flexible enough to accommodate tidal ranges, and durable enough to function for months under constant use. The team spent 6 months on preliminary designs before realizing that no existing technology could meet the requirements. They would have to invent everything from scratch. The concrete solution. The breakwater problem was solved first because it was the most critical. Without protection from Atlantic waves, no harbor system could function. The team needed barriers capable of stopping 12-foot waves while being transportable across the channel. The solution was Phoenix caissons, massive concrete boxes that would be towed to Normandy, flooded, and sunk in predetermined positions to create an artificial reef. The engineering was brutal. Each caisson measured 200 feet long, 60 feet wide, and 60 feet tall. They weighed 6,000 tons when empty, 7,000 tons when flooded. They required construction precision measured in inches, despite their massive scale. The design specifications read like architectural fantasy. The concrete walls had to be 10 feet thick at the base, tapering to 3 feet at the top. Internal compartments would control flooding during placement. Flood too quickly, and the caisson would sink uncontrollably. Flood too slowly, and tides would shift it off position. The base had to be perfectly flat to ensure stable placement on the seabed. The interior had to include pumps, valves, and control systems to manage placement. And they needed 150 of them. Construction began in October 1943 at sites across Britain. Dry docks that normally built destroyers were converted to caisson production. The Thames estuary became a caisson factory, with units being constructed in specially built basins, floated out at high tide, and towed to staging areas. The scale was industrial warfare applied to construction. Concrete was mixed and poured 24 hours daily. Steel reinforcement was fabricated in dedicated factories. Quality control inspectors verified every dimension because any error would create a weak point that Atlantic storms would exploit. The caissons were marvels of practical engineering. Each unit included compartments that could be flooded independently, allowing precise control during placement. Anti-aircraft guns were mounted on top because the caissons would be towed across the channel and needed defense against German aircraft. Crew quarters were built inside because teams had to live in the caissons during towing and placement. Navigation lights were installed because the tow across the channel would occur at night under blackout conditions. Chief Engineer Hugh Yoris Hughes, supervising caisson construction, described the scale. "We were building concrete islands that would be towed across the channel and placed with surveyor precision while under German artillery fire. Each caisson represented more concrete than used to build a typical office building, yet had to float, be towed at 3 knots, and survive North Atlantic conditions. The engineering tolerances were fighter aircraft precision applied to structures the size of apartment blocks. The concrete itself was revolutionary. Standard maritime concrete wouldn't survive the thermal cycling, wave impact, and corrosion of the North Atlantic environment. Engineers developed a new formulation using granite aggregate, extra Portland cement, and chemical additives that created concrete with compressive strength exceeding 5,000 pounds per square inch, higher than most structural concrete used in buildings. The reinforcement was equally advanced. Each caisson contained over 300 tons of steel reinforcing bar, positioned to create a structural cage that would distribute loads evenly. The steel couldn't simply be placed, it had to be precisely positioned, tied in place, and inspected before concrete was poured. Any deviation could create stress concentrations that would crack the caisson under load. By April 1944, 146 Phoenix caissons were complete, staged at locations around the British coast, ready for towing. The largest engineering project in British history was ready for the next phase, crossing the Channel. But the caissons were only the outer barrier. Inside that barrier, the Allies needed to build an actual harbor. The floating pier revolution. The pier problem was more complex than the breakwater. Ships needed to dock at piers that remained stable despite 18-foot tidal ranges. Conventional piers were rigid structures supported by pilings driven into the seabed. The Mulberry piers had to float, rise and fall with tides, support 40-ton tanks driving across them, and remain operational in storm conditions. The solution came from Alan Beckett, a civil engineer who'd spent years designing bridges. His insight was to reverse conventional thinking. Instead of building piers that resisted tidal movement, build piers that accommodated. The design used a series of floating steel roadways called whales, supported by cruciform steel pontoons called beetles. The beetles were engineering marvels, steel pontoons 60 feet long and 25 feet wide, with a cruciform cross-section that provided exceptional stability. They displaced enough water to support a roadway plus vehicles, yet were light enough to be towed individually. Each beetle was ballasted to float with its deck 2 feet above water at high tide, 20 feet above water at low tide. As tides rose and fell, the beetles rose and fell, keeping the roadway consistently above water. The whales were equally ingenious. Flexible steel roadways, 560 feet long and 24 feet wide, with steel grating that allowed water to drain while providing traction for vehicles. Each whale weighed 180 tons and could support 40-ton tanks at 25-mile-per-hour transit speeds. The articulation system was the breakthrough. The whales were connected to beetles by universal joints that allowed the roadway to rise and fall with tides while maintaining horizontal orientation. The joints used spherical bearings that could rotate in 3 axes, absorbing wave motion, tidal changes, and structural loading without binding. The design allowed 18 feet of vertical movement while maintaining roadway grade within 2 degrees. Testing occurred in the Thames estuary under conditions that terrified everyone involved. A full-scale mock-up was assembled. 3 beetles supporting 1 whale, anchored in tidal waters, loaded with 40-ton tanks. The tanks were driven across repeatedly at varying speeds, while engineers measured deflection, stress, and fatigue. The structure performed perfectly. The roadway flexed with waves, rose and fell with tides, and supported vehicles that would have sunk conventional floating platforms. But a single pier was useless. The harbor needed 6 miles of these flexible roadways, connecting to shore through the tidal zone, extending to deep water where ships could dock. The scale was staggering. 200 beetles and 86 whales for each harbor, each component precisely manufactured, individually towed across the channel and assembled under fire. Major Alan Beckett, designing the final assembly procedures, faced the ultimate engineering challenge: describe in written procedures how to assemble a floating harbor on a hostile beach while under artillery fire, using equipment towed across the channel by exhausted tugboat crews, working in tidal waters with underwater obstacles, all while maintaining positioning accuracy measured in feet. His solution was brilliant in its simplicity: color-coded assembly diagrams that looked like children's toys instructions, but represented the most complex maritime construction project ever attempted. Each beetle was numbered, each whale lettered, each connection point marked. Assembly crews needed only to match numbers and letters. No advanced engineering knowledge required, just the ability to follow illustrated instructions under artillery fire. The Gooseberry Gambit. The Phoenix caissons provided storm protection, but they took weeks to position properly. The invasion couldn't wait weeks for harbor facilities. The Allies needed immediate breakwater protection, something that could be in place within hours of landing. The solution was audacious: sink ships deliberately to create instant breakwaters. The Gooseberry Harbours used corn cobs, old merchant ships and obsolete warships that would be sailed to Normandy, positioned precisely, and scuttled in shallow water to create barriers against storm waves. The concept was simple. The execution was terrifying. 60 ships were selected. Old merchant vessels, worn-out cruisers, obsolete battleships, and ships damaged beyond economical repair. They ranged from 1,500-ton coastal steamers to the 25,000-ton battleship HMS Centurion. Each ship was prepared for scuttling, cargo removed, unnecessary equipment stripped, scuttling charges placed in hulls, navigation equipment installed for the final voyage. The crews who sailed these ships to their graves were volunteers. They would pilot aging vessels across the channel, navigate through minefields and obstacles, position their ships with surveyor's precision, trigger scuttling charges, and escape before their ships sank beneath them. The operation required seamanship of the highest order. Deliberately sinking your ship in exactly the right position is harder than keeping it afloat. Commander Donald McGregor, assigned to sink HMS Durban, described the mission. We would sail to Normandy, position within 50 feet of our designated coordinates, open the sea cocks, and abandon ship as she settled. If we missed position, we'd create a gap in the breakwater that storms would exploit. If we positioned too early, tides would shift us. If we positioned too late, we'd interfere with following ships. The margin for error was measured in minutes and feet. The corncobs were sailed to France beginning on D-Day itself. Within 48 hours, 23 ships had been scuttled at Gold Beach, creating a 3-mile breakwater. Within a week, all 60 corncobs were in position at 5 invasion beaches, providing immediate storm protection while Phoenix caissons were being positioned. The deliberately sunken fleet included vessels with distinguished service histories. HMS Centurion had fought at Jutland in 1916. HMS Durban had escorted Arctic convoys. Dozens of merchant vessels had carried cargo for years. Now they would serve one final mission, dying in position to protect the invasion. The sinkings were conducted with ceremonial precision. Ships' flags flew as they were positioned. Crews saluted as they abandoned ship. The vessels settled into the sand with dignity, their superstructures remaining above water, creating barriers that would protect Allied shipping for months. The Channel crossing. The logistical challenge of towing the Mulberry components across the Channel exceeded the complexity of the invasion itself. Between D-Day and D+18, over 400 separate components had to be towed from British staging areas to Normandy beaches. 146 Phoenix caissons, 200 Beetles, 86 whales, 60 corncobs, and thousands of tons of anchoring equipment, all moved by 132 tugs across 100 miles of ocean. The towing operation began on D-Day +1 and continued for 3 weeks. Each caisson required 2 ocean-going tugs to move it at 3 knots, slower than walking speed, but the maximum safe towing velocity for structures that weren't designed for propulsion. The crossing took 24 hours in calm weather, 36 hours if conditions deteriorated. The caissons had to navigate through mine-swept channels, avoid German E-boats, and arrive at Normandy with sufficient daylight remaining for positioning. The tug crews worked under conditions that would have broken peacetime sailors. They operated for days without rest, crossing the channel repeatedly, towing structures that could become uncontrollable in storms, navigating by dead reckoning when radio silence was mandatory. The tugs were small vessels, typically 500 to 800 tons displacement, towing loads that outweighed them 10 to 1. A caisson breaking loose in a storm could capsize the tug towing it. 3 caissons were lost during towing. Phoenix Unit Number 23 broke loose in mid-channel during a gale on June 13th. The towing hawser parted under strain, and the caisson drifted into a minefield where it struck a mine and sank. Phoenix Number 47 developed flooding in heavy seas and foundered before reaching France. Phoenix Number 91 was rammed by a landing craft in darkness and sank near the French coast. but 143 caissons completed the crossing successfully. Each arrival at Normandy required precision positioning using surveying techniques adapted for maritime use. Survey teams had placed marker buoys at each caisson position, 146 precisely plotted locations where caissons would be sunk to form the breakwater. Positioning teams would guide tugs to the correct location, verify position with optical surveying equipment, signal the caisson crew to begin flooding, and monitor placement to ensure the caisson settled vertically. The flooding process took 90 minutes per caisson. Internal compartments were flooded in sequence to maintain stability as the structure settled. If flooding occurred too rapidly, the caisson would tilt and fall over. If flooding was too slow, tides or currents would push it off position. The crews manning the flooding valves were working inside a structure that was deliberately sinking beneath them, timing their escape to the final moments before the caisson became uninhabitable. Lieutenant Commander Bernard Holgate supervised caisson placement at Gold Beach. We were sinking 6,000-ton concrete islands in 60 feet of water, positioning them within 2 feet of target, while German artillery fired at us from inland positions. The caisson crews remained inside until the last possible moment, ensuring proper flooding sequence. I watched men climbing out of access hatches as water rose around them, the caisson settling into position beneath their feet. The courage required was extraordinary. They were deliberately sinking the structure they stood on, trusting that the mathematics and engineering were correct. By June 18th, all Phoenix caissons were positioned. 2 3-mile breakwaters protected the harbors, creating sheltered water where ships could anchor safely. The next phase could begin, installing the floating piers. Assembly under fire. The pier installation occurred while the beachhead was still under German artillery attack. Teams worked around the clock, positioning beetles, connecting whales, anchoring the structures against tides and currents. Each connection point required precision measured in inches. Misalignment would create stress concentrations that would fail under load. The beetles were positioned first, moored with 8-ton anchors connected by chains to the pontoon structure. The positioning was calculated to create a roadway that would remain level across its length despite tidal variations. At high tide, the beetles would be closer together longitudinally. At low tide, they would spread apart. The whales would flex to accommodate this movement while maintaining roadway grade. The whale installation was the critical step. Each 180-ton roadway section had to be floated into position, lifted by crane ships, and lowered onto the beetles. The articulating joints had to be connected precisely. Any misalignment would bind the joint, preventing the roadway from moving with tides. Installation teams worked in all weather, day and night, because delays meant supplies couldn't flow and the invasion would stall. By June 16th, the first piers were operational at Armoured, Mulberry B. Ships were unloading vehicles and supplies onto floating roadways that rose and fell 18 feet with tides while maintaining horizontal orientation. The system worked perfectly. Trucks drove from ships to shore across piers that moved vertically but not horizontally, exactly as designed. Then the Great Storm hit. June 19, 1944, the storm that should have ended everything. The worst channel storm in 40 years struck on June 19th with winds exceeding 40 miles per hour and waves reaching 8 feet. The storm lasted 3 days, during which the invasion supply operation should have collapsed. Ships couldn't unload, landing craft couldn't beach. Conventional wisdom said the invasion would stall, giving the Germans time to reinforce and counterattack. The Mulberry Harbours saved the invasion. At Omaha Beach, Mulberry A, the American harbor, was less complete than its British counterpart. Fewer caissons were in position. The pier systems weren't fully connected. When the storm hit, components broke loose. Whales broke free from beetles. Caissons shifted position. Within 48 hours, Mulberry A was destroyed, reduced to wreckage strewn across the beach. At Gold Beach, Mulberry B survived. The Phoenix caissons held position, creating protected water behind them. The whales flexed with the waves but didn't break. The beetles rode out the storm, rising and falling with swells but remaining anchored. The articulating joints performed exactly as designed, absorbing motion that would have shattered rigid structures. When the storm passed on June 22, Mulberry B remained operational. Ships resumed unloading immediately. The harbor had survived conditions that would have prevented any supply operation using conventional landing craft. The British forces received 11,000 tons of supplies during the storm period, not as much as calm weather would have allowed, but enough to sustain operations and prevent the Germans from exploiting the weather delay. The storm validated every design decision. The flexible piers that seemed over-engineered proved necessary. The massive caissons that seemed too expensive proved essential. The redundant anchoring systems that seemed excessive proved adequate. The Mulberry Harbours did exactly what they were designed to do: maintain supply operations under conditions that would defeat conventional methods. American forces, having lost Mulberry A, diverted their supply operations through Mulberry B. The single remaining artificial harbor supplied both British and American forces until Cherbourg was captured on June 26. Even after Cherbourg fell, it took weeks to clear German demolitions and make the port operational. During that period, Mulberry B supplied 2 armies. The numbers that tell the story. Between D-Day and the end of September 1944, Mulberry B handled 2.5 million men, 500,000 vehicles, 4 million tons of supplies. The harbor operated continuously for 10 months, far exceeding its designed lifespan of 3 months. At peak efficiency, it handled 12,000 tons of cargo daily, equal to a major peacetime port. The construction statistics were equally staggering. 2 million tons of concrete used, 1.5 million tons of steel fabricated, 45,000 workers employed, 40 million pounds spent, equivalent to $6 billion modern currency. 18 months from concept to operational deployment. The project consumed resources equivalent to building 50 destroyers or 1,000 heavy bombers. Critics argued these resources should have been devoted to weapons production. The counter-argument was simple. Without the Mulberry Harbours, the invasion would have failed, rendering all other weapons production irrelevant. The German miscalculation. German intelligence knew the Allies were building something unusual. Reconnaissance aircraft photographed strange concrete structures in British harbors. Agents reported construction activity at dockyards normally used for warships. But German analysts couldn't believe the intelligence. Surely the Allies weren't building portable harbors. The concept was too ambitious, too expensive, too operationally risky. General Feldmarschall Erwin Rommel, commanding German forces in France, based his defensive strategy on a simple assumption. The Allies would need to capture a deep-water port within days of landing. Therefore, the invasion would target a port city, most likely Calais or Cherbourg. Rommel fortified these locations with everything available, creating fortress zones designed to hold for weeks while counterattacking forces assembled. The German defensive plan depended on logistics strangling the invasion. Even if the Allies secured beachheads, they couldn't sustain operations without port facilities. The Wehrmacht would counterattack while Allied forces were still dependent on vulnerable beach supply operations. The plan was sound, based on historical precedent and logistical reality. The Mulberry Harbours invalidated every assumption. The Allies didn't need to capture a port. They brought their own. The invasion landed on beaches the Germans considered unsuitable for sustained operations. By the time German intelligence understood what was happening, 2 complete artificial harbors were operational and supplying 2 armies. Rommel's first mention of the Mulberry Harbours appeared in a report dated June 8. Enemy has established artificial harbor facilities at invasion beaches using prefabricated components towed from England. Scale is larger than initially believed. Facilities appear capable of sustained operations. Previous assumptions about enemy supply limitations were incorrect. By June 15, German intelligence had revised their assessment. Enemy Mulberry Harbours represent major engineering achievement. Concrete breakwaters provide protection equivalent to natural harbors. Floating pier systems accommodate tidal ranges while supporting heavy vehicles. Installation under combat conditions demonstrates industrial capacity exceeding our estimates. Recommend immediate action to destroy these facilities. German artillery targeted the Mulberry Harbours constantly. Luftwaffe bombers attacked when weather permitted. Neither effort succeeded. The harbors were too large to destroy with available weapons. Individual components could be damaged, but the overall system remained functional. And the British defended Mulberry B with anti-aircraft batteries, fighter patrols, and smoke screens that made accurate bombing impossible. The engineers who made it real. Behind the Mulberry Harbours were thousands of engineers who turned theoretical concepts into operational reality. They worked without computers, using slide rules and hand calculations to design structures that pushed material science to its limits. Their names aren't famous, but their contribution was decisive. Major Alan Beckett designed the articulating pier system that solved the tidal range problem. His equations describing the mechanical behavior of flexible piers under dynamic loading became standard reference material for maritime engineering. Brigadier Bruce White coordinated the overall project, managing 45,000 workers, reconciling design conflicts, and making real-time decisions about resource allocation. His administrative achievement was as impressive as the engineering, keeping the project on schedule while managing competing demands from military planners, construction contractors, and resource allocation authorities. Chief Engineer Hugh Joris Hughes supervised caisson construction, maintaining quality control across multiple construction sites while meeting deadlines that allowed no delays. His insistence on rigorous inspection procedures ensured that caissons would survive North Atlantic conditions. These men and thousands of others worked in obscurity, solving problems that had no precedent, creating solutions that had never been attempted. When components arrived in Normandy and performed exactly as designed, they vindicated 3 years of calculations, testing, and manufacturing precision. The legacy that lasts. The Mulberry Harbours remained operational until November 1944, when natural port facilities were fully restored and the artificial harbors were no longer needed. Mulberry B was partially dismantled, with components towed back to Britain for reuse. Many Phoenix caissons remained in place, gradually settling into the seabed where they still rest today. The technological innovations pioneered for Mulberry influenced post-war engineering. The flexible pier designs led to developments in offshore oil platforms. The large caisson construction techniques informed harbor development projects worldwide. The project management methods became standard for large-scale engineering projects. But the most significant legacy was strategic. The Mulberry Harbours proved that engineering innovation could overcome operational constraints considered absolute. The Germans built their defense on the assumption that the Allies were bound by conventional logistics. The Allies changed the rules by building logistics systems that didn't exist. This pattern would repeat throughout the remainder of the war. When faced with obstacles, American and British engineers didn't accept limitations. They designed solutions. The Manhattan Project, Pluto Pipeline, Habakkuk aircraft carrier proposal all reflected the same philosophy. Impossible was a challenge, not a limit. The museum where history rests. Today, sections of the Mulberry Harbour remain visible at Armoured, France. Phoenix caissons still sit on the seabed where they were sunk in June 1944. The concrete has weathered 80 years of storms, tides, and wave action, yet remains structurally intact. Testimony to engineering quality that exceeded requirements by orders of magnitude. The Muséum du Débarquement at Armoured contains scale models, photographs, and salvaged components. Visitors can walk to the beach and see caisson sections protruding above water at low tide. The structures that seemed temporary in 1944 have become permanent memorials. A small plaque near the museum entrance bears an inscription from Churchill's original memo proposing the project. They must float up and down with the tide. Don't argue the difficulties. The difficulties will argue for themselves. Below that quote is a simple statistic. 2.5 million men, 500,000 vehicles, 4 million tons of supplies. June 1944 to November 1944. Mulberry B, Gold Beach. The numbers don't capture the full achievement. The artificial harbors weren't just logistics, they were confidence. They told every soldier landing in France that the invasion wouldn't be abandoned, that supplies would flow, that the planners had thought through every problem and solved it. The Germans had calculated that the invasion would fail because Allied logistics couldn't sustain it. They were correct by every conventional measure. The Allies simply refused to accept conventional measures. They built harbors where harbors couldn't exist, towed them across an ocean, assembled them under fire, and kept them operational for 10 months. The final accounting. Churchill's crazy idea required 146 Phoenix caissons, totaling 1.5 million tons of concrete, 60 corncob block ships deliberately sunk, 200 beetle pontoons, 86 whale flexible roadways, 10 miles of floating pier, 132 tugs to tow components across the channel, 45,000 workers constructing components, 18 months from concept to deployment, 40 million pounds in 1944 currency. The return on that investment, the invasion succeeded. 2 armies supplied for 5 months, 2.5 million men landed, 500,000 vehicles delivered, 4 million tons of supplies transported. The Western Front established, Nazi Germany defeated. Without the Mulberry Harbours, D-Day logistics would have depended on capturing ports that the Germans had fortified specifically to resist capture. The invasion might have succeeded anyway, but the cost would have been dramatically higher, the timeline longer, and the outcome less certain. Major General Harold Bull, Eisenhower's operations chief, stated in his post-war report, "The Mulberry Harbours were the single most important factor in the invasion's logistics success. Without them, we would have been dependent on beach landings and captured ports. The Germans would have had weeks to counterattack before our logistics were secure. The harbors gave us supply capacity that the Germans couldn't interdict. That made all the difference." In 1985, on the 41st anniversary of D-Day, a group of British engineers who'd worked on the Mulberry project returned to Armoured. They walked along the beach where Phoenix caissons still protruded from the sand. One engineer, Harold Hickling, who'd supervised pier construction in June 1944, stood looking at the remains of structures he'd helped build 40 years earlier. A reporter asked him if he was proud of his work. Hickling's response captured the engineering mindset. Proud isn't the word. We did what was necessary. They told us to build harbors that could be towed across the channel and assembled on hostile beaches. We said yes and got to work. The harbors worked. The invasion succeeded. That's not pride. That's professional satisfaction that our calculations were correct. The reporter pressed, "But you built something unprecedented, something that experts said was impossible." Hickling shook his head. Experts said it was impractical, not impossible. There's a difference. Impractical means expensive, risky, and difficult. We had budget, we accepted risk, and we solved the difficulties. That's engineering. He gestured at the caisson remains. Those structures were designed for 3 months of service. They've been here for 40 years. The concrete is still solid. The design is still sound. We overbuilt everything because failure meant the invasion would fail. That's not genius, that's taking requirements seriously. The interview ended with Hickling walking to the water's edge and touching one of the caissons. He said, "We did this. A team of engineers working with slight rules and hand calculations built structures that changed history. And they're still here, still solid, still proof that engineering can solve any problem if you refuse to accept that something is impossible." The equation that won the war. The German defensive strategy was mathematically sound. Allied invasion requires port facilities. Capturing fortified ports takes weeks. German counterattack would destroy beachhead before ports were secured. Therefore, invasion will fail. The equation had one flaw. It assumed Allied logistics were bound by conventional port infrastructure. The British added a new variable. Allied invasion plus artificial harbors equals secure logistics. Secure logistics plus sufficient supplies equals sustained operations. Sustained operations plus reinforcement equals breakthrough. Therefore, invasion succeeds. The Mulberry Harbours weren't just engineering, they were strategic mathematics. By changing the logistics equation, they invalidated German defensive calculations. Rommel's forces were positioned to defend ports that the Allies didn't need to capture. By the time German commanders understood this, the invasion was irreversible. The men who built roads on water. The crews who assembled the Mulberry Harbours under fire never received decorations comparable to combat soldiers. They were engineers, tugboat operators, construction workers, and logistics personnel. They didn't storm beaches or fight in hedgerows. They built piers, positioned caissons, and connected whales to beetles while German artillery fired at them. Petty Officer James Crawford served on a tug towing Phoenix caissons across the channel. We made 4 crossings in 12 days, towing 2 caissons each trip. The crossings took over 24 hours in good weather, longer when storms hit. We navigated by dead reckoning through mine-swept channels, dodging E-boats and air attacks. When we delivered a caisson to Normandy, German artillery would fire at us while we positioned it. We'd release the tow, get clear, and head back to England for the next one. It wasn't heroic, it was seamanship under difficult conditions. Leading seaman Michael Hartley operated a beetle during pier assembly. We lived on the beetles for weeks, riding them up and down with the tides, connecting whales during brief periods when weather permitted. The Germans shelled us regularly. We'd hear the whistle of incoming rounds and hope they'd miss. Mostly they did. When they hit, we'd patch damage and continue working. Stopping wasn't an option. Ships were waiting to unload, troops needed supplies, and delays meant people died. So we worked through storms, artillery fire, and exhaustion, because that's what the mission required. These men understood their role. They weren't combat heroes, they were professionals doing difficult work under dangerous conditions. Their contribution was measured in tons of supplies delivered, vehicles unloaded, and operations sustained. It wasn't glorious, but it was essential. The closing truth. On June 6, 1944, 156,000 men stormed 5 Normandy beaches in the largest amphibious invasion in history. Their courage was extraordinary. Their sacrifice was immense. Their achievement was historic. But courage alone doesn't win wars. Logistics wins wars. The men on the beaches needed ammunition, fuel, food, medical supplies, and reinforcements. They needed those supplies to flow continuously, reliably, in sufficient quantities to sustain operations regardless of weather or enemy action. The Mulberry Harbours provided that flow. 2 million tons of concrete, towed across the channel, assembled under fire, and operational within days. Flexible steel roadways that rose and fell with 18-foot tides while supporting 40-ton tanks. Engineering solutions to problems that conventional wisdom considered unsolvable. Churchill's crazy idea made D-Day possible by solving the one problem that threatened to make it impossible: sustained logistics across open beaches in North Atlantic weather. The Germans calculated that problem was insolvable. The British refused to accept that calculation. The Mulberry Harbours represent the ultimate triumph of engineering over circumstance. When faced with requirements that seemed impossible, British engineers didn't argue. They calculated, designed, tested, built, towed, assembled, and operated structures that changed the course of history. 80 years later, those structures still sit on Normandy beaches where they were placed in June 1944. The concrete has outlasted its designers. The engineering has outlasted the empire that built it. The Phoenix caissons remain as permanent monuments to temporary solutions that worked so well they became eternal. The silent testimony. At low tide on Gold Beach, visitors can walk among the caissons. The concrete is weathered but solid. Marine growth covers the surfaces. Rust stains mark where steel reinforcement is exposed. But the structures remain fundamentally intact. 6,000-ton blocks of concrete that have survived 80 years of storms that would have destroyed lesser construction. French marine archaeologists surveying the sites in 2019 were surprised by the structural condition. Dr. Laurent Carpentier, leading the survey team, reported, "We expected significant deterioration after 75 years of exposure to Atlantic conditions. Instead, we found concrete that remains structurally sound, with compressive strength measurements still exceeding modern construction standards. The engineering quality was extraordinary. These structures were built to last 3 months and have lasted a quarter of a century." The survey used ground-penetrating radar and sonar to examine caissons below the waterline. The findings revealed the extent of over-engineering. The concrete walls were thicker than necessary by modern calculation. The steel reinforcement was denser than required. The foundations were more massive than structural analysis demanded. The engineers had built margin into every component because failure wasn't acceptable. This philosophy, building excessive strength into structures whose failure would be catastrophic, became standard practice in critical military engineering. The Manhattan Project facilities, the radar stations of the DEW Line, the ICBM silos of the Cold War all reflected the same principle. When failure means disaster, over-engineering is prudent design. The American lesson. The loss of Mulberry A at Omaha Beach provided its own lessons. The American harbor was less complete than the British installation when the June 19th storm hit. Fewer caissons were positioned. The pier connections weren't fully secured. When the storm struck, the incomplete harbor couldn't withstand the forces. Post-storm analysis revealed the failure mechanisms. Incomplete caisson placement had left gaps in the breakwater that allowed storm waves into the protected area. Those waves created surge forces that overstressed the pier connections. The whales, unsupported by sufficient beetles, flexed beyond their design limits and fractured. Once the first connections failed, cascading failures destroyed the entire structure within hours. The lesson was unforgiving. Partially completed engineering solutions often perform worse than no solution at all. A complete system has redundancy and load sharing. An incomplete system has stress concentrations at the missing connections. The British harbor, more complete when the storm hit, survived because every component was in place and sharing the loads. American forces, pragmatic as always, responded by expanding their use of LSTs, landing ship tank, beached directly on shore. These vessels, designed to beach themselves and unload directly onto sand, became the primary American supply method after Mulberry A's destruction. The approach was less efficient than a proper harbor, but more robust than a partially completed one. The irony wasn't lost on military planners. The Americans, famous for their engineering prowess, had lost their artificial harbor, while the British, who'd invented the concept, kept theirs operational. The difference wasn't capability, it was completion. The British had prioritized full installation before the storm hit. The Americans had prioritized rapid partial operation. When the storm hit, completion defeated speed. General Omar Bradley, commanding American forces, acknowledged this in his memoir. "We rushed to get Mulberry A operational, accepting incomplete installation to begin supply flow immediately. The British took longer to complete Mulberry B, but finished the job properly. When the storm hit, their patience was vindicated. Our haste cost us the entire harbor. It was a lesson in the value of thorough engineering over expedient shortcuts." The unbuilt Mulberries. The success of the Normandy harbors led to proposals for similar installations in other theaters. Plans were drawn for artificial harbors to support the invasion of Japan, including designs for harbors that could survive Pacific typhoons. Engineers proposed advanced versions with improved caisson designs, stronger pier systems, and better anchoring against the more severe Pacific weather. The designs were never built. The atomic bombs ended the Pacific War before Operation Downfall required artificial harbor construction. The engineering plans were filed away, the materials allocated elsewhere, and the specialized knowledge dispersed as engineers returned to civilian life. But the planning revealed how far the technology had evolved. The proposed Pacific Mulberries would have been larger than the Normandy versions, with caissons designed to withstand 20-foot waves, pier systems capable of 25-foot tidal ranges, and anchoring systems proof against 100-mile-per-hour typhoon winds. The engineering calculations exist in archives, testimony to solutions developed for problems that never materialized. Captain John Hughes Hallett, naval commander involved in Mulberry planning, reflected on the unused designs in a 1952 interview. "We learned so much from Normandy that the next generation of artificial harbors would have been dramatically superior. Improved caisson designs, better pier articulation, stronger materials. But we never built them because the war ended. In some ways, that's the best outcome. The knowledge exists if ever needed again, but the need hasn't arisen. Engineering capability without the necessity to use it. That's victory." The technology that disappeared. The specialized skills developed for Mulberry construction largely vanished with the end of the war. The engineers who designed the caissons retired. The workers who built them moved to other industries. The tugboat crews who towed them across the channel dispersed to peacetime shipping. Within a decade, the institutional knowledge existed only in archived documents and aging memories. Modern attempts to recreate Mulberry-type structures have encountered this knowledge gap. When oil companies explored floating platform designs in the 1960s, engineers studying the Mulberry archives found calculations whose reasoning wasn't documented. The designers understood principles that weren't written down because they seemed obvious to engineers working daily on the problems. Dr. William McDonald, structural engineer reviewing Mulberry designs in 1967, described the frustration. "The calculations are correct. We can verify that by testing. But the intuition behind certain design choices isn't documented. Why did they use specific concrete mixtures? Why were reinforcement patterns arranged in particular ways? The answers worked, but the reasoning wasn't preserved. We've lost the tacit knowledge that made the explicit designs succeed. This pattern repeated across many World War II technologies: the Manhattan Project, radar development, proximity fuse design, all involved knowledge that existed in the minds of engineers and wasn't fully captured in documentation. When those engineers retired or died, the knowledge went with them. The loss wasn't catastrophic. Modern engineers can analyze existing structures and deduce principles, but rediscovery is slower than preservation. The Mulberry Harbours represent the last time certain construction techniques were used in practice. The techniques are documented, but not fully understood. The understanding could be recovered, but the urgency that drove the original development no longer exists. The economic reality. The Mulberry Harbours cost £40 million in 1944, approximately $6 billion in 2025 currency. This expenditure, enormous by any standard, represented roughly 1% of total British war spending in 1944. The cost was justified by a simple calculation. If the harbors enabled the invasion to succeed, they were worth any price. If the invasion failed, the cost was irrelevant because Britain would lose the war. Post-war economic analysis questioned whether the investment was optimal. Could the same resources have produced more weapons, trained more soldiers, or supported different operations? The counterfactual is unanswerable. We know the invasion succeeded with the Mulberry Harbours, but can't know if alternative approaches would have succeeded differently. What's certain is that the Mulberry Harbours achieved their mission with margin to spare. They were designed to operate for 3 months and functioned for 10. They were designed to handle 12,000 tons daily and achieved that capacity regularly. They were designed to survive channel storms and survived the worst channel storm in 40 years. By any engineering standard, they exceeded specifications. The return on investment was strategic rather than economic. The harbors didn't generate profit, they enabled victory. Calculating their value requires assessing the probability that the invasion would have succeeded without them, the consequences of invasion failure, and the value of victory versus defeat. Those calculations involve variables that resist quantification. Military historian Max Hastings addressed this in Overlord. The Mulberry Harbours were a strategic insurance policy. They might not have been strictly necessary. The invasion might have succeeded using captured ports and beach supply, but they eliminated logistical uncertainty from the invasion planning. Eisenhower knew he would have port capacity regardless of how quickly Cherbourg fell. That certainty affected every decision. You can't calculate the value of eliminating uncertainty from the most critical military operation of the war. The German engineers' view. After the war, German engineers who'd observed the Mulberry Harbours were interviewed about their assessment. Their responses revealed professional respect mixed with strategic despair. Dr. Heinrich Müller, German civil engineer who'd analyzed Allied construction throughout the war, stated, "The Mulberry Harbours demonstrated industrial capacity we couldn't match. Not because German engineering was inferior, our engineers were excellent, but because we lacked resources for such projects. Building 2 complete artificial harbors while simultaneously conducting global war exceeded our capacity. The British and Americans could afford strategic engineering insurance. We could only afford battlefield weapons." The assessment was accurate. Germany had excellent engineers and sophisticated construction capabilities, but German industry was stretched, sustaining armies on multiple fronts, replacing losses from strategic bombing, and developing new weapon systems. There was no surplus capacity for projects like Mulberry. The strategic implications were profound. The Mulberry Harbours represented military strategy that assumed abundance rather than scarcity. German strategy was built on scarcity management, achieving maximum effect with limited resources. Allied strategy was built on abundance application, throwing sufficient resources at problems to ensure solution. Neither approach was inherently superior, but abundance won. When both sides had excellent engineers and skilled workers, the side with more resources could afford larger, more robust solutions. The Mulberry Harbours were excellent engineering enabled by abundant resources. The workers who built history. The 45,000 workers who constructed Mulberry components represented a cross-section of British society. Many were women, drawn into heavy construction work by wartime labor requirements. Others were men too old for military service or in reserved occupations. Some were soldiers on engineering duty. Together, they built the largest construction project in British wartime history. The working conditions were industrial warfare. Concrete was mixed and poured continuously, 24 hours daily, 7 days weekly. Steel reinforcement was fabricated in specialized shops, transported to construction sites, positioned within caissons, and tied in place. Quality control inspections verified every dimension, because any error could cause catastrophic failure. Accidents were frequent. Heavy construction involves dangerous machinery, high weights, and complex operations. During caisson construction, 23 workers were killed in industrial accidents, crashed by equipment, struck by falling materials, or drowned when caissons being flooded for testing flooded too quickly. These deaths received no publicity. They were doing civilian jobs under wartime urgency. Their sacrifice was statistical rather than heroic. But their contribution was essential. The engineers designed the structures. The workers built them. Without skilled labor transforming calculations into concrete and steel, the Mulberry Harbours would have remained theoretical concepts. The workers who tied rebar, poured concrete, and assembled forms were as necessary to victory as the soldiers who stormed the beaches. Margaret Hutchinson, who worked on caisson construction at age 19, recalled the experience in a 1994 interview. "We knew we were building something important for the invasion, but we didn't know what. The caissons were just concrete boxes to us, very large concrete boxes that required precise construction. We worked long shifts, 6 days weekly, with Sunday as our only rest. The work was hard, the hours were long, and the pay was modest. But everyone knew the invasion was coming and that these structures were somehow critical. That knowledge kept us working when we were exhausted." She continued, "After D-Day, they told us what we'd built. The caissons we'd constructed were towed to France and used as artificial harbors. I remember feeling proud that our work had contributed directly to the invasion's success. We weren't fighting, but we were helping those who were. That felt important." 50 years later, I visited Normandy and saw one of the caissons still sitting on the beach. I couldn't know if it was one I'd worked on, but it might have been. That possibility was moving. Something I had helped build at age 19 was still there at age 69, still solid, still serving as a monument. The environmental legacy. The Phoenix caissons remaining at Armoured have become artificial reefs supporting marine ecosystems that wouldn't exist without them. The concrete surfaces, initially sterile, were colonized within years by algae, barnacles, mussels, and other marine organisms. These primary colonizers created habitat for fish, crustaceans, and other species. Within decades, the caissons supported thriving ecosystems. Marine biologists studying the sites have documented over 80 species living on or around the caissons, more biodiversity than exists on adjacent natural seabed. The vertical surfaces created by the caissons provide habitat types that wouldn't exist on the relatively flat sandy bottom. Crevices in the concrete shelter juvenile fish. The structure disrupts bottom currents, creating areas of slower water flow where sediment accumulates and different species can establish. The unintended environmental benefit doesn't diminish the structure's historical significance. It adds another dimension. The caissons were built for war, succeeded in their mission, and now support life. The transformation from weapons of war to habitat for marine species is poetic in ways the engineers never intended. French environmental authorities have designated the caisson sites as protected marine habitat. Fishing is restricted. Diving is permitted only under controlled conditions to prevent damage. The structures that were built to last 3 months and have lasted 80 years may last another century or more, serving as both historical monuments and environmental assets. The modern comparison. In 2023, engineers analyzing the logistics requirements for major disaster relief operations studied the Mulberry Harbours as historical precedent. When ports are damaged or non-existent, how do you establish supply chains for millions of people? The Mulberry solution, bring your own port, remains relevant. Modern technology could build artificial harbors superior to the WW2 versions in most respects. Modern materials are stronger. Modern construction techniques are faster. Modern positioning systems are more accurate. A modern Mulberry could be smaller, lighter, and more capable than the 1944 version. But modern Mulberries would cost dramatically more in relative terms. The 1944 project consumed 1% of British war spending. An equivalent modern project would cost $60 to $80 billion at similar relative scale. Democratic governments struggle to authorize such spending for projects without immediate necessity. The WW2 Mulberries were built because invasion failure meant national extinction. Modern democracies rarely face comparable existential urgency. The comparison reveals what enabled the original Mulberry Harbours, not just engineering capability, but political will to commit enormous resources to solving a problem that threatened national survival. Modern engineering could replicate the technical achievement. Modern politics might not replicate the resource commitment. The children who played on history. For decades after the war, French children played on the Phoenix caissons protruding from Gold Beach. The structures became playground equipment, concrete islands to climb on, tidal pools to explore, mysterious chambers to investigate. The children had no understanding of the structure's historical significance. They were just interesting concrete things on the beach. Local residents used the caissons as fishing platforms, picnic sites, and navigation markers. Tourism operators incorporated them into historical tours. Artists used them as subjects for paintings and photographs. The structures became part of the local landscape, so familiar that their remarkable origin story was easy to forget. This domestication of military history is natural. Weapons of war become tourist attractions. Battlefields become parks. Fortifications become playgrounds. The Mulberry caissons followed this pattern, from critical military infrastructure to historical monuments to simple landscape features. Each generation experiences them differently. But preservationists worry about the gradual erosion of historical context. As veterans die and memories fade, the structures risk becoming just old concrete blocks on a beach rather than monuments to engineering achievement that enabled victory. Maintaining historical context requires education, interpretation, and active preservation of the stories behind the structures. The Musée du Débarquement works to preserve this context through exhibitions, educational programs, and documentation. School groups visit to learn about the invasion. Historians research the engineering details. Veterans' descendants come to see what their grandfathers built. The effort to maintain historical memory continues even as living memory fades. The engineering philosophy. The Mulberry Harbours embodied an engineering philosophy that can be summarized simply: when something must work, over-design everything. The structures weren't optimized for cost, weight, or efficiency. They were optimized for reliability under worst-case conditions. This philosophy clashed with peacetime engineering, which balances performance against cost. Peacetime harbors are designed to be economical, sufficient strength with minimal excess. The Mulberry Harbours were designed to be certain, excessive strength to guarantee success. The difference was existential stakes. Modern engineering still faces this choice. Commercial projects optimize for cost-effectiveness. Critical infrastructure projects optimize for reliability. Space systems optimize for mission success regardless of cost. The Mulberry approach, massive over-design to eliminate risk, remains relevant when failure is unacceptable. The concrete walls, 10 feet thick, when analysis suggested 6 feet would suffice. The steel reinforcement, 50% denser than calculations required. The anchoring systems, 3 times stronger than maximum predicted loads. Every component built with margin, because the engineers understood they were calculating for conditions they couldn't fully predict. This conservative approach saved the harbors during the June 19th storm. The storm exceeded design conditions, but the over-design margin absorbed the excess. Structures built to minimum requirements would have failed. Structures built with 50% margin survived. The lesson persists. When you're building something unprecedented for conditions you can't fully predict, optimism in design is catastrophic. Pessimism in design, assuming everything will be worse than expected, is prudent engineering. The unsung heroes. The Mulberry Harbours succeeded because thousands of people did difficult jobs competently under difficult conditions. The dramatic achievements, the concept, the designs, the scale, receive attention. The mundane achievements, the execution, the details, the persistence, enable success but generate less recognition. The tugboat crews who crossed the channel repeatedly, towing loads that could capsize them if anything went wrong, the survey teams who positioned caissons within feet of targets while artillery fired at them, the construction workers who poured concrete in winter cold and summer heat, the quality control inspectors who rejected work that didn't meet specifications even when schedules demanded compromise. These people weren't heroes in the conventional sense. They were professionals doing jobs that required skill, dedication, and courage. Their names aren't recorded in histories. Their contributions are acknowledged statistically: 45,000 workers, 132 tugboat crews, uncounted survey teams and construction specialists. But historical outcomes depend on such people. Wars aren't won by generals and politicians alone. Wars are won by tugboat operators who navigate safely, by workers who build correctly, by inspectors who maintain standards. The Mulberry Harbours succeeded because thousands of people did their jobs well when failure meant catastrophe. This is the truth that monuments can't capture. Great achievements depend on competent execution of necessary tasks. The Mulberry concept was brilliant. The Mulberry execution was professional. Both were necessary. Neither alone would have succeeded. The final storm. In November 1944, a second major storm struck the Normandy coast. By then, Cherbourg was operational, Le Havre was being cleared, and Antwerp had fallen. The Mulberry Harbours were no longer critical to Allied logistics. But they'd achieved their mission, bridging the gap between invasion and port capture, sustaining 2 armies through 5 months of operations. The November storm caused additional damage to structures already worn by months of continuous use. Some pier sections broke loose, several caissons shifted position, But the British didn't repair the damage. The harbors had served their purpose. Natural ports could now handle the logistics load. Partial dismantlement began in December 1944. The most valuable components, the beetles and whales, were recovered and towed back to Britain for potential reuse. The caisson complex were too large and heavy to economically recover. They were abandoned in place, left as monuments or obstacles depending on perspective. Some local French authorities wanted the caissons removed, arguing they were navigational hazards and eyesores. Others wanted them preserved as historical monuments. The debate continued for years before preservationist sentiment prevailed. The caissons would remain, protected as historical sites. The decision ensured that physical evidence of the Mulberry achievement would persist. Without the caissons, the story would exist only in documents and photographs. With the caissons remaining visible, visitors could see the scale and understand the ambition. The structures became their own best evidence. The conclusion. On June 6, 1944, the fate of Western Europe hung on logistics. Could the Allies supply an invasion force across open beaches in North Atlantic weather? German strategists calculated the answer was no. British engineers calculated differently. The engineers won the argument by building proof. 2 complete artificial harbors operational within days of the invasion, handling 12,000 tons of supplies daily, surviving the worst Channel storm in 40 years, and sustaining 2 armies for 5 months. The numbers tell part of the story. 2 million tons of concrete, 146 Phoenix caissons, 60 corncob block ships, 200 beetle pontoons, 86 whale roadways, 10 miles of floating pier, 45,000 workers, 18 months from concept to deployment, 10 months of continuous operation, 2.5 million men landed, 500,000 vehicles delivered, 4 million tons of supplies transported. But numbers don't capture determination. Someone had to believe artificial harbors were possible before anyone knew how to build them. Someone had to design structures for conditions they couldn't test. Someone had to build components with precision measured in inches despite unprecedented scale. Someone had to tow concrete islands across a submarine-infested ocean. Someone had to assemble floating piers under artillery fire. Thousands of someones did all of this and succeeded. The Mulberry Harbours represent engineering at its most consequential, not laboratory experiments or theoretical breakthroughs, but practical solutions to immediate problems where failure meant disaster. The engineers who designed these structures weren't seeking knowledge, they were ensuring victory. 80 years later, the Phoenix caissons remain on Gold Beach, where they were positioned in June 1944. The concrete is weathered, the steel is corroded, but the structures stand solid, testament to engineering that exceeded requirements so thoroughly that temporary solutions became permanent monuments. At the Armoured Museum, a final display panel contains a quote from Brigadier Bruce White, the chief engineer who coordinated the entire project. Written in 1946, reflecting on the achievement. We were told to build portable harbors that could be towed across the channel and assembled on hostile beaches. Every expert said it couldn't be done. We said, define the requirements and we'll engineer the solution. The requirements were defined. We engineered the solution. The harbors worked. That's all there is to say. Engineering isn't about doing impossible things. Engineering is about solving difficult problems through calculation, design, and execution. The Mulberry Harbours were difficult. They weren't impossible. The difference matters. Below that quote is a photograph taken on June 8, 1944, 48 hours after D-Day. It shows British troops driving trucks across a whale roadway toward the beach with ships unloading in the background, and Phoenix caissons visible along the horizon. The sea is rough, the sky is gray, but the logistics are flowing. The photograph caption is simple: "The crazy idea worked." And because it worked, the invasion succeeded, France was liberated, Nazi Germany was defeated, and Western Europe remained free. All because engineers refused to accept that portable harbors were impossible. They built them anyway. They towed them across the channel. They assembled them under fire. And they kept them operational while two armies used them to conquer a continent. The Mulberry Harbours made D-Day possible. The engineers made the Mulberry Harbours real. And the concrete remains, 80 years later, proof that impossible is just difficult that nobody's solved yet.